So physicists tell us tales of mystical quantum field theory. It only goes by the name, the 2-0 theory in 6th dimension. The 2-0.
Can I just make a suggestion?
Yes, not to write on the board.
To write with black.
Not with that marker.
Not with that. Is it black anybody? This is our friend. 2-0. OK, so this is what it's called. It hasn't been constructed to our satisfaction. It doesn't have a Lagrangian. We don't really know what it is. All we have is the kind of lore passed to us by the brave pioneers of the subject who first charted this thing. And so we will call it instead theory X, a little more friendly. And we're going to see what we can get out of this theory, out of some kind of coarse axiomatics we found from the founders and from our best resource, which is Andy and Tudor and Kevin. So I'd like to introduce you to what I call the X games. So I'm going to introduce the rules of the game very kind of sporadically and without any claim to consistency or completeness. So whenever I need another rule, I will make it up. But the idea of the game is that we're going to start life in 6 dimensions. And we're going to go down from dimension 6 down and down until we get to something we understand. So how does X start life? It starts life as a 6-dimensional superconformal quantum field theory, which I don't know what it is, so we'll leave it at this. But what is the data associated? So the data is going to be G an A, D, E Lie algebra, simply laced Lie algebra. And to any such simply laced Lie algebra, we're going to, so in other words, there's types AN, DN, E6, E7, E8, simply laced Lie algebra. So to each one of these, there's going to be assigned some 6-dimensional field theory. And we won't have anything to say about theory X in 6 dimensions. The secret to success in this business is the circle. So we're going to have some idea of what this theory does on geometries in which there's circles around. So in other words, we're going to look at 6-dimensional space in which one direction is periodic. And so maybe this is we need some visual aids. So we have to, and I'll need some help putting this up. So this is the board game for the X game. Yeah, so, OK, we'll get some tape. So we're going to play this game over the course of the week. There we go. Yeah, so I took my 4-year-old son to a marionette show this weekend, and professional amazing marionette show, and his reaction to seeing this professional amazing marionette show is to go home and start making his own marionettes, and that's what we spent all weekend doing. And so I kind of got inspired by that. It's sort of how I feel like when I listen to Andy doing his amazing things, and then I go home and try to play the game on my own. Figured I could try to make my own version of this. So we're going to try to, so our goal, maybe, is that enough? Or is that going to, OK. So what we're going to do is we're going to try to fill in as much of this chart as we can over the week. This is also my attempt to one-up Greg Moore's poster on the conference page. So what is so the idea is this, the theory starts in 6 dimensions. Here's the dimension that we're in. Now, when we go down to 5 dimensions, the theory all of a sudden becomes something that has a name. So we'll write the name. When we reduce the theory on the circle, we get 5-dimensional super Yang-Mills theory associated to a group G. So most of these will just be names or be black boxes. So now what is that? So one thing that's already happened here is that a group has come out. So that's one thing that's a little confusing about the theory, and one of the many things I'll kind of sweep under the rug. Oops. Which color am I using? Black. OK. So you can ask, what is G? And G is going to be, what is G? Well, it's going to be a group of type ADE. We've chosen a Lie algebra, and we're going to have a group of that type. Now, you can ask which one. Yeah.
You already have a Lie algebra there.
That's right.
This G has nothing to do with it.
It's, yes. So that's right. Right. So we're going to have a group. Now, you can ask still which one. And that's part of one of the secret rules of the game. So the idea is that this theory X is not a plain old vanilla quantum field theory, whatever that is. It's what you might call X is relative quantum field theory. So I referred to a recent paper of Fried and Telemann. What this means basically is that in order to give the value of X, I need to make some auxiliary choices. Those auxiliary choices are something, if I look at a 6 manifold, it's going to be something like a Lagrangian inside of H3 of my 6 manifold with coefficients in what, Andy? Something. In the center?
In the center, yeah.
Center. Great. And some lattice. And so in any case, there's some extra choices that are taking place around circles. And so secretly, one of my secrets when I have circles is I'm making a choice of some Lagrangians in the 6 manifold, and that's picking me a group. Another way to say this less confusingly is that what theory X produces for a manifold is a collection of outputs, one depending on various data, including the choice of a group with that given Lie algebra. OK, so that's part of the setup. In fact, if you're coming down the hill from MSRI and you don't like just simply laced Lie algebras, you can also get non-simply laced Lie algebras along the circle. You can get non-simply laced Lie algebras by non-simply laced groups by doing to get types B, C, what's left? A, F, G. We can twist by a Dinkin diagram automorphism as we go around circle. Now, this doesn't make any sense at all, but the idea is that there's some extra data we can do around a circle that's going to help us choose not just a Lie algebra, but also a group, not even a group of the type ADE, but the group of type of a fixed points of a Dinkin diagram automorphism, which gives us all the other types. So we can get everything we want. So OK, so let's start playing the game. So what do we know? Well, OK, I haven't even told you what kind of a beast it is. One of the things we're going to work with this, we'll work with this theory X in a twisted setting, in a setting that was pioneered by Gayota, Moore, and Neitzke. And the idea is that we're not going to try to understand a full quantum field theory in flat space, but we're going to think of this as so we're going to look at our 6 manifold, and we're looking at our 6 manifold of the form of 6 manifolds of the form of a 2 manifold cross a 4 manifold. Well, most of our geometry will be of this kind. And we're going to do a twisted form which depends holomorphically on this. So this is going to be some Riemann surface. So we can get a conformal field theory in 2 dimensions here, and depends topologically on this 4 manifold. So there's a version of theory X. So what I'm going to take to start my game, I'm going to have a theory that depends holomorphically on 2 dimensions and purely topologically on 4 dimensions. So that's going to be the beast. So one way to think about that is if I give you a Riemann surface sigma, I'm going to get a 4-dimensional topological field theory attached to sigma. I'll think of this as a machine giving 4-dimensional topological theories attached to Riemann surfaces.
The 4D manifold also splits into 2D times a 2D manifold. How does it know which part is supposed to be holomorphic and which part is supposed to be holomorphic?
Well, I told it. I mean, I start with a 4 manifold, with a 6 manifold, and I'm giving you some data. Right? There's some decoration of the data. This 6 manifold has a type which is a Riemann surface cross a 4 manifold.
I'm just saying there should be some intrinsic data associated to this 6 manifold.
Well, there's an intrinsic structure which is it's a 6-dimensional conformal field theory, which doesn't discriminate. And in Kevin's talks, and I don't know, maybe other talks will have something that's less discriminatory. In my talks, I'm going to fix 2 of those dimensions to be holomorphic, and then make it topological in the other 4. So I don't need to think about any structure in the other. I do have to twist that in the other 4 dimensions. It's just a topological field theory. And so the idea is that you give me so the game that we want to play here is you start with a Riemann surface, and you get a 4-dimensional topological field theory, and we are going to try to describe what these field theories are on various backgrounds. And that's going to be what we'll try to do. And so these field theories have names. So here are some Riemann surfaces I wrote down on this row. If I look at my 6-dimensional field theory and I reduce it on various Riemann surfaces, I get various gauge theories in 4 dimensions, which I'll give names. And these names at this point don't mean very much. This is something called n equals 4 super Yang-Mills. This is the field theory that's studied in the work of Kapustin and Witten relating to geometric Langlands. Andy will be upset with me, but I'm going to write here n equals 2 super Yang-Mills. Pure. This is the theory that's related to Donaldson theory. Secretly, that's not quite a 2-sphere. It's a 2-sphere with some little decorations on it, but I'm going to ignore those. So these are 2 of the basic field theory when people talk about gauge theory. This is Donaldson theory. This is the geometric Langlands theory. These ones are the theories that were studied by Gallardo, Moore, and Knightsky, and they call these class S theories. And we'll hear more about them in Andy's lectures, I think. And this one, if I look at a 2-disk with some particular boundary conditions, let me call this Kovanov-Witten. This is a 4-dimensional topological theory that Witten explains Kovanov homology. So we'll see Kovanov homology appearing out of this study. So here are some names for some of these 4-dimensional field theories. OK, so now what I'd like to do is start the math. So what I'd like to do is, so what we're going to spend much of today and probably next time talking about is just how are we going to think about 4-dimensional field theories. So I'm going to just a second. So I'm going to forget about theory X for a second. Though if people have particular dots on the board they want to fill in, we can. You want to skip ahead, we can do that. But then we're going to start some math. Yeah.
I was wondering what the difference between C2 and sigma was going to end up being.
Not much. So sigma, somehow or S2 and sigma for that matter. So I'm thinking sigma is usually going to be a hygienous surface. Okay. But in some slots down here, I just got lazy and just wrote a sigma to include any surface. So some things I'm going to maybe tell you something specific. Or if you'd like, n equals 4 super Yang-Mills is a special class S theory. It's the class S theory attached to the 2 torus. If you look at the 2-sphere with the irregular puncture, you get the class S theory is that. So sigma is just kind of a catch-all for surface. Okay. Yeah?
So is the twist of theory X reduced to those theories that you've written on the board, or is it that the twist reduces to some twist of theories that you've written?
So really, I don't know anything about non-topological theories. So I'm kind of imagining everything is done topologically. Again, Andy might tell you, to get the statements on this row, you don't need to do any twist. You don't need to do the topological twisting. So n equals 4 super Yang-Mills is a full, 4-dimensional supersymmetric quantum field theory. I'm only going to think about it as a topological field theory and doing some twisting on it. But so yeah, I don't know if that's relevant to your question or not. So these are names for things I'm going to. So at every point in the way I'm going to play the game is I'm going to put some theory in each slot, which depends on these data, but probably a lot more data too. So, sorry, was that the question?
Yeah, I think.
Okay.
I mean, it's true that the names you wrote are the names that people usually attach to the untwisted.
That's right. That's right. Except for the Kovanov-Witten one, probably. But yeah. Yeah. Okay. Other questions before we go on? Maybe I'll just write one more in advertisement for Andre's talks. We might get here is going to be Chern-Simons theory. So there's your 3 dimensions. Is going to appear over there. So that's a 3-dimensional field theory that we'll learn more about later today. Okay. Any other questions? Okay. So let's. So let's get started. So now I want to tell you how I think about topological field theory. And so we're going to write down some axioms, some structure of what a field theory is. and then some examples, and we'll try to work our way to see what to put in all these slots. But we need some repertoire of what kind of answers we might hope to get first. So I'm going to think about topological field theory in the framework of the Bordism hypothesis, proved by Jacob Lurie. And so, what does it mean? Topological field theory for me, well, topological field theory is something I'll denote Z. It's a symmetric monoidal functor. It's a symmetric monoidal functor out of board N, which is going to be the Bordism higher category of N manifold. Bordism higher category of manifolds. And it's going to come with some adjective here. So the adjective here might be framed or oriented or spin or some other kind. So we're going to look at a Bordism theory of manifolds with some structure. We're going to make them consider them as a symmetric monoidal category with disjoint union. And we're going to look at representations of this structure, just maps out of that. And we can specify where we want to map it to later. So what kind of a thing is, so let's forget about the target. Let's think about the source. What kind of a thing is this board N? So the objects, so we can start from the bottom. So when we think about the objects, you can think about them as being points. But when we think about them points, or think of them as zero manifolds, but we're going to really be thinking about them. Where's the N? The N it's going to be important to keep track of the N. So these are points, zero manifold, but endowed with an n-dimensional tangent bundle. So we kind of stabilize these to dimension n. So we look at, so this is somehow the difference of notation between mathematicians and physicists. A mathematician might say a point. A physicist might say Rn. When I draw Rn, I'm really going to think about this as maybe a point with a n-dimensional tangent space. So we're going to, instead of drawing pictures like points, it's going to be more useful to draw unions of Rn's, which I'm thinking of as very, very non-compact n manifolds. So rather than think of this as being zero manifolds, I'll think about these as just unions of Rn's. And so what are the morphisms, the one morphisms between these guys? Well, they're going to be cobordisms with the same structure. They're going to be Bordisms, I guess, whatever it's called. Bordisms with the same kind of structure, so I can draw my unions of points. So this is a morphism from 3 points to 3 points. But I'm going to think about these as, I'm going to stabilize these and think them as always as being n manifolds. So in other words, so if you'd like, you take your favorite picture of a Bordism, and I'm just going to cross. So it's a usual picture of a Bordism, but crossed with Rn minus 1. So I'm always going to cross with Rn just to get to the top dimension. And then I can say what kind of structure I want. If it's framed, if it's oriented, if it's spin, these are all structures on this n-dimensional tangent bundle. Okay. When we get to, so for example, if you look at Bordisms from the empty set to the empty set, so in other words, if you look at closed one manifolds, we have several versions. So connected, so when you look at, say, connected closed one manifolds, in this setting, we have several of them. We have, I mean, these are versions of the circle, but I can have, fortunately, I can't really draw, so it's a problem. So this is S1 cross Rn minus 1. This is one version of the circle, but another, so this is one version of the circle we'll be interested in. Another version of the circle we'll be interested in is the annulus. And again, topologically, these are the same, but as framed, so let me just call this the annulus. But as framed n manifolds, these are going to be, so here I guess I was drawing n equals 2. These are going to be two different framed 2 manifolds. And of course, you can have more interesting twisty things, but I won't try to draw. OK. So these are our one morphisms. And now what are our n morphisms? You just keep going.
So here the analysis framing is coming from the blackboards.
That's right. That's right. And think of this as being a subset of the plane. So I'm taking the plane and I'm removing a little disk and I'm getting the induced framing, while this is the product framing. So this is the product. This is the framing that comes just from thinking of this, if you like, as a one manifold and then stabilizing. This is really a kind of honestly two-dimensional kind of framing. And there's a Z worth. There's a bunch of others. Okay. Yes.
So you wrote like what, S cross Rn minus 1?
Yeah.
Could you also have a non-trivial n minus 1 dimensional?
That's right. Yeah. So my Bordisms, my one morphisms are just going to be one manifolds with boundary with an n-dimensional tangent bundle. So I'm endowing them with an n-dimensional tangent bundle, and it's going to be with whatever structure, framed, oriented, or et cetera. Could be anything. So I'm thinking of this really as being an n manifold. An n manifold, if you'd like, that's allowed to have kind of one compact direction. My zero morphisms were n manifolds with no compact directions. And as I go up, I'm going to have more and more compact directions. But I'm always thinking of them as n manifolds. Okay. Okay. And so
I still don't understand why you call it tangent bundle.
Because I'm thinking of this as an n manifold. I'm thinking of having here's a two manifold, and how do I want to write this as a composition of morphisms? So this is going to be a two morphism. It's going to be a two morphism from this one morphism to this one. So this is a one morphism from the empty set to the empty set. So one morphism from the empty set to the empty set. Suppose I want to write it as a composition, then I can pick out two circles. And the point is that all the manifolds that I get in the process really come with n-dimensional colors. So this is in a two-dimensional field theory. All the manifolds, when I see one manifold in this picture, it's always coming as a colored picture of a two-manifold. So that's going to tell me how to. So if I was looking at oriented field theory, you usually don't ignore this. You ignore this extra data. Now, suppose I was trying to do Bordism with manifolds with a lot more structure. In order to glue, I really need germs of n manifolds. Just in the setting of oriented manifolds, there's not a lot of structure to the germ of a one manifold and a two manifold. But that's really the picture. It's always germs of everything inside is really n manifolds, but they're germs of it. So here it's a germ of a now as a framed two manifold. This could be so. For example, this circle and this circle. So to David's question, I could also remove a little circle here, and these circles are different as framed. If the picture is somehow framed, then these will be different framed circles. So that's the notion of K-morphism. K-morphisms are going to be Bordisms of Bordisms of Bordisms of Bordisms. And the composition is gluing. So this is how you glue. Because I've chosen colors and everything, think of them, I can glue them together. Okay.
Will you really get non-trivial, like the circle has a non-trivial line bundle on it. Would you really ever get that as a
I don't know. Tell me.
No, I'm not asking whether it would occur. Of course, it can occur. Like,
yeah.
I'm just asking, that's allowed by your rule?
Sure.
Okay.
I mean, if it's any framed, yeah,
okay.
Yeah. So we'll see when we talk about invariance in two-dimensional field theory. If they'll have infinitely many invariants.
To repeat Alex's question, like the crossing was just an example of this.
Yeah.
Okay.
Yeah. Crossing is somehow the easiest example. There's always a way of stabilizing by crossing, and there'll be more interesting ones. Like this one is a different one. Right? This is the annulus framing.
But I meant the underlying topological, underlying bundle, not just the framing.
I don't know.
All right, we'll.
Yeah.
Could you just tell me what the data is again? It's a K manifold,
Mm-hmm.
and then you're given an n bundle over it, which splits as the tangent bundle to that K manifold plus some other guy. That's the data?
Sounds good. All right. Yeah. I mean, I think I just wanted the data is just going to be germs of closed K manifolds inside n manifolds. That's, I think, the right with a given structure. That's, I think, the. Okay. so we have a notion of gluing, which is composition of these bordisms. So I won't write down all the acts, and we'll see some pictures. But one thing that's going to be useful to keep track of, important to keep track of, if I look at maps in this bordism category between two manifolds, what kind of beast is this? The maps between two manifolds I want to remember as a topological space is really going to be a topological space. And when I think about topological space, I'm really thinking about a homotopy type. So I'm not going to care about the exact geometry of the space. It's going to be the homotopy type of a space. If you prefer to think about this combinatorially, you can think about it as a simplicial set. And what is that idea? So for example, so let me just draw what I mean. So if you look at maps from two circles to one circle in a two-dimensional picture, so here's my, so here if I'm looking at a two-dimensional field theory, I want to look at maps between these cylinders. Well, this is going to be a disjoint union over various topological types. So this is joint union over, well, there's all kinds of topological types I can think of putting inside, various, for each genus, for each, so then, let me write it this way, the union over the topological type of classifying space, of classifying spaces of the corresponding manifold. So for example, if I look at inside of here, for example, I have B diff of the pair of pants. So there's a particular bordism between two circles to another circle, which is the pair of pants. But there's a whole topological space of pairs of pants. That's all I'm saying. That when you look at a pair of pants, you can decide where you put the two circles. They can move around each other. And so there's a whole topological space of this, and keeping track of this topology is going to be important. So I don't care about the geometry, but the homotopy type of this is something interesting. I guess it's a circle. OK. So that's the idea that inside it, when we look at morphisms in this category, we're going to keep track of topology, topology of the space. And so this gives us what we're going to think of as this is kind of the structure that we have on board N. So board N with this joint union, it's again some kind of adjective, say framed or oriented, and the empty set as the unit. This is going to be a symmetric monoidal, well, technically, I guess, infinity N category. So it's a higher category, and the infinity is just standing in for the fact that I have these topological spaces. The N is the fact that I have bordisms of bordisms of bordisms. The infinity is saying that I'm keeping track of topological spaces of maps. OK. And OK, so now let's, so now what is an n-dimensional topological field theory? We want to look at a functor. Again, we have a symmetric monoidal functor, a functor from board N to some other beast of the same kind, some other tensor category. And so what does this mean? This means that we have an assignment for every n manifold. Maybe it's a color around various lower dimensional manifold, but to everything in here. So these are all n manifolds of various amounts of compactness. To every such n manifold, I'm going to attach some object, something in C. It's an assignment that, and it's going to respect respecting disjoint union. So disjoint union of manifolds will go to tensor product in C. It respects composition of morphisms. In other words, it respects gluing. So if I have a composition of morphisms, like we had before, we have a gluing where we glue one manifold to another one. That corresponds to a composition in this category. So by being a functor, it means it goes to composition here. And what else does it respect? And it respects the topology of the Helm spaces. So these Helm spaces are topological spaces. Typically, we're going to be thinking that C, the maps in C maybe don't have any topology. So that means, so if C is discrete, if the maps in C don't have interesting topology, This just means that we have an assignment that's not constant, but locally constant on these Bordism spaces. That's what respecting the topology will mean. We have the construction will be a locally constant construction in these Bordism spaces. OK. So, so what can we? So let's see what kind of thing. So what's the idea? The idea. So what am I going to take for C? I'm not really want to specify C very precisely, but I'm going to say what's the idea that Z of a closed N manifold. So suppose I have a closed N manifold. So in physics, this is supposed to stand in for some. I'll write a caricature. It's supposed to be integral over some space. This is fields, integral over space of fields of the field theory on M. It's going to be some space of fields, and we have something which we'll denote incredibly schematically as e to the I s of phi d phi. So there's some kind of action and some kind of mythical measure that we're going to integrate the action over the space of fields. It's exponential action over the space of fields, and that's what we call the z of m, the partition function. All I'm going to take right now out of this caricature is it's a number. So to closed N manifold, I want to attach numbers. Okay. So though actually we'll see later that that's not actually what I want to do. But anyway, so that's the idea. So to closed N manifolds, you want to attach numbers. So the N morphisms in C are going to be complex numbers. So we're going to have a kind of a C-linear object. Now. Now, what about if I take an n-1 manifold? What is the physics meaning for this? So n-1 manifold, and again, I'm really thinking of it. I'll often drop the cross R's. If I write a lower dimensional manifold, I'm secretly thinking of it cross R. So what do I think of this? So here, this is going to be what in physics will be the Hilbert space of the theory. So what does that mean? It's I'm going to think about it. So this is the Hilbert space of the quantum field theory. How does that? So this is the Hilbert space on N of this quantum field theory. So what does that mean? Our caricature again for this, everything is in quotes. I guess the whole lecture series will be in quotes. But so it's some kind of space of functionals. So the idea is I'm thinking that I have some notion of fields. Functionals on fields. So you look at fields on this N manifold, and you look at functionals on it. Now, just to make things a little more interesting, I'm going to think of this not as a vector space, but as a differential graded vector space. So I'm going to think that I have some differential called d sub q, and q is supposed to denote something that's coming out of the physics origin. Maybe this is some supercharge coming from supersymmetric field theory. For now, it's just a differential. It's an operator with square 0. So we have a vector space, and you can think of this as maybe something like a Delbar differential. So I'm going to really secretly be looking at maybe holomorphic functionals, or maybe Durham differential. Maybe I'm going to be looking at some kind of locally constant functionals. Okay. And then there's some kind of grading. There's going to be a grading, which is some kind of U1 charge or fermion number, if it's a Z grading, or maybe it's a fermion number, which is a Z mod 2 grading. This is just to say that the kind of vector spaces that we get naturally come as differential graded vector spaces. We're going to be interested not in just discrete vector spaces, but in differential graded vector spaces. And sometimes they'll be Z graded, sometimes they'll be Z mod 2 graded. OK, so that's somehow the character. I want to say that I have, I assign, can I erase this? So we have a differential graded vector space attached to an N manifold. So that, in other words, my n-1 morphisms should be vector spaces, or better, DG vector spaces. And what's the relation between the two? That if I give you an n manifold and an n-1 manifold appearing at its boundary, how should they relate? I want to say that the partition function of an n manifold, which is not a closed n manifold, but an n manifold with a closed boundary, rather than getting a number, it's going to be a vector in Z of n. So how should you imagine this? So we said that Z of n is a functional So it's something that attaches a value. It's functionals on fields. So in other words, for every field, I should give you a number. And that, let me call it phi sub n, just to specify this is a field on n. And that's going to be an integral over fields such that field restricted to n is phi sub n, the same thing, e to the minus is of phi d phi. Okay? So I do a relative version where I fix the boundary value. Yeah.
So see the Zn cross R is the Hilbert space on there?
This is going to be the Hilbert space. I mean, a Hilbert space taking poetically. It's
So
a vector space.
question, should that be Z of n cross R?
Yeah, I'm going to drop the r's when at random points.
Also, the
Yeah.
fields, are the fields also in quotations here, or should we be thinking of
They
a
are.
precise notion of fields on n?
Sorry?
Like, are
Well,
fields like
we'll give examples. So the idea is that secretly you have this idea of a field theory. You have some notion of spaces of fields on n manifolds, whether or not they're compact. So n here is really an n manifold. It's just not, there's always a little n. So we have some notion of fields on n manifolds.
And typically that's like some sections of a bundle, or
Yeah, we'll give examples, but there'll be things like there might be maps into some target. That's kind of the easiest example. There might be principal bundles with connection, maybe. Those are kind of two of the main examples. So we look at functionals on the space of fields, and the idea is that we can construct elements in this functional space if you give me a manifold with boundary. With boundary m, it's just this kind of relative version of that path integral, where you fix. The notation makes sense?
yeah.
Okay. Yeah. Okay. Yeah.
So what's the interpretation of Z of n minus 1 that's not
It's a thing. Yeah. Yeah.
Can you say it precisely?
Probably. I mean, I just don't want. I'm not. It's going to be. It's still a space of. I mean, it's still a space. I mean, it's still this, right? I mean, it's still a space of functionals on the space of fields. I mean, the interaction. So that you ask, how does it interact with anything? I mean, it's always a space of functionals on fields of M. And maybe let me draw one more picture to suggest. So let me generalize this picture for a second. And the more useful version is, suppose I give you M, which is a Bordism from N1 to N2. So now you can include more interesting things as Bordism. So I'm going to think of fields of M as a correspondence. So if I have a field of M, I can restrict it to the two boundary components. I think of restricting a field to either of the two boundary components. And then I think of writing an integral transform. So this definition generalizes to say what the fields of a manifold M, they give me operations. So Z of M is now going to be a map from Z of, so I have a map from Z, so I'm going to linearize integral transforms as maps. That's the map associated to the cobordism. And what is this map? It's the same notion, but let me just write it down. It's a Fourier transform or integral transform. It's so Z of M attached to a functional on N1 that has a value on a field on N2, right? You start with a functional on fields on N1, and you can evaluate the result on a field on N2. And that is going to be the integral over fields such that field on N2 are fixed of F N1 evaluated on the field phi restricted to N1 times e to the minus, I don't know what this is, minus I, whatever. Okay, and which is probably a lot more confusing than just writing it formally. That's saying that Z of M is pi 2 lower star, pi 1 upper star of blank with the integral kernel, which is e to the is. Okay, so that's the integral transform. Okay, so that's how manifolds talk to each other. Bordisms will be linearized to integral transforms.
Sorry, so in
Yeah.
particular, if I have an n-1 manifold with a non-trivial extra line bundle over it, you're saying to that I should associate the same vector space. It's just the morphisms will be different?
That's probably a little stronger than I want to commit to, right? The functionals are really they're functions on the color. I mean, depending on the linearization, it might depend on the color. I mean, again, I think n-1 manifolds are roots. They're never here. It's all about n manifolds. And maybe your functional deck doesn't actually depend on the coloring data, but that's up to you. OK. All right. So now one thing to say about this is this construction. Now let me just one little thing is that this is locally constant. This construction is supposed to be locally constant over the moduli space, B diff of M. This is the moduli of M's. So you have the space M. You have a locally constant over B diff of M. So you have a family of such maps. You take the space M. There's a family of manifolds all diffeomorphic to M. This is the universal family of manifolds diffeomorphic to M. And you have a construction like this that's required to be locally constant. That's part of being this field theory. So in other words, what this really means is that it's going to extend to a map from chains on B diff of M. So these are really differential graded vector spaces. So I can ask for something that Z of M is a map that I really get a map like this. So as I look over the moduli space of M's, I get every M is a point in here. It's a zero chain. But if I give a Bordism of these zero chains, I get well, you know what a chain map is, right? Okay. So that's part of the data, just encoded in saying that I have this topological field theory. I keep track of these topological spaces of homes. OK. Any questions about this? Yeah. Here it should be. Yeah. Here it should be the moduli space of these guys. Yeah. B diff rel boundary. OK. So that's what a field theory. Now I'm going to give a lot of examples, but I want to get down to one more dimension before we start giving examples. Partly because I don't like numbers. So you'll see this bottom row is kind of left pretty empty. So we want to get a little more room too. So if we want to get to n-2 manifolds, so in other words, things with n-2 compact directions and 2 non-compact directions. So what we want is, we want something which is, you might call, if you like topology, you might call it delooping of DG vect. So we want something which is just an annoying way of saying that the HOMs should be DG vector spaces. If you like. Endomorphism, really, we want some category C where endomorphisms of the unit in C are going to be DG vector spaces. Because we already knew that for a closed n-1 manifold, so a closed n-1 manifold is an endomorphism of the empty n-2 manifold. And we knew we wanted DG vector spaces there. So we have to choose something such that maps from the empty set to itself are DG vector spaces. And there are two kind of choices, and they're both going to play a big role. So there's two common popular choices. I mean, of course, you can have your own favorite choice. But two popular choices are, I'm going to take this 2 category, which is going to be the category of DG categories. You can ignore the DG if you don't like it. So just think of the 2 category of categories, where the maps are, again, I'm going to write DG. Look at differential graded, look at functors between categories, and look at natural transformations. That's a 2 category I can put here, which has this property. So I can, to an n-2 manifold, I might think that I'm attaching a category. And so in this picture, I'm going to think that Z of an n-2 manifold is going to be some kind of category, or DG category, of sheaves on fields of Pn-2. Before we had some kind of functionals, now we have functionals valued in vector spaces. So vector space valued functionals on the space of fields. So that's going to be a useful choice. There's a more concrete choice. If you don't like categories, category is kind of a multicolored version of an algebra. So instead of, if you don't like categories, you can replace these with algebras. So you can think of another category, which is differential graded algebras. And here, again, I'm going to think about my algebra. If I think in this picture, I'll think of Z of Pn-2 would be some ring of functions on the space of fields, on fields of Pn-2. But now I'm keeping track of them as a ring with multiplication. that could be my caricature for my ring of functions. But the important thing is what the morphisms are. If I want DG algebras, I really want the morphisms to be differential graded bimodules. So I don't want a map of algebras. I want to allow more general bimodules. And again, maps of bimodules. So these are two natural places where you can work. And what's the relation between these? Well, this is well known, but it's going to be useful for us later. So in algebra, what's an algebra? There are two ways to think about it for us. It's going to be you can think about it as a category with one object. If I give you say a C-linear category or a DG category with one object, then it's in dimorphisms form an associative DG algebra. So that's one relation between the two. Or another way that might be more useful, an algebra is a category that's generated by one object. So this is somehow maybe a better relation. It's not to think of categories that only have one object, but categories that are generated by an object. So what's the... So just to spell this. Mm-hmm.
When you say Sheaves on these fields, where does the framing come in?
Well, again, the space of field depended on the framed manifold.
Okay.
So there's a space which is space of fields on the frame manifold, and now I'm going to linearize it as sheaves, or if you want an algebra, I think of functions on it. And now you can tell already that that's not always as good. If the space is not affine, then looking at functions is not as rich as looking at sheaves. So that's the dictionary I want to spell out because it's going to be important for us later.
Is it correct that if you start with theory X and you decide once and for all you're going to go down to 5 dimensions with S1, then everything you'll ever see from there will have this flavor of being first Bordisms, then fields, then some linearization?
That's yes and no. I mean, somehow, any slot that I'm going to be able to tell you a name for it, that name will depend on writing that in that way. That the field theory, there'll be some notion of space of fields. There'll be a space of linearization. On the other hand, there might be many ways there might be interesting dualities that are not of that form. So the object might be of the form, but the morphisms are not of the form. So same slot might be described in different ways via spaces of fields and linearizations, and might be that will be a lot of interesting equivalences.
So you're saying that everything you'll discuss will fall into this rubric of
That's right.
Bordisms, fields, linearization.
That's right.
May fall into this rubric
In more than one way.
more than one way.
That's right. That's right.
That would be very interesting.
It will be very interesting, and maybe just to keep people entertained, that where we hope to go. I'm not sure we'll get. Well, the goal of these talks might be, for example, to explain all the structures that we love up the hill, namely the geometric Langlands program. So the whole geometric Langlands program is going to be explained in this slot. So there is going to be something where you attach space of fields and so on, but that slot has some symmetry. In particular, there's a 2 torus, which has an SL2Z symmetry. And that symmetry is manifest in theory X, but it won't be manifest in this kind of field theoretic description. So that's going to be important. So it's important that that's sort of not what a field theory is, but it's a way of describing a field theory.
But you won't discuss anything where there isn't at least some classical
Yeah, that's right.
field.
Yeah. No, I have no idea what. Everything I will discuss is going to be of that kind. Other questions?
When you write DJ algebras, bimodules and interfiners, you mean that objects are representations of these DJ algebras, and bimodules are.
Well, right. So yeah. So let me. That's where I'm getting to. That's the relation between these two rows. Okay. So let me let me spell that out. So let's say if I give you an algebra A, I can attach to it a category, A mod. And in this category, there's a distinguished object called A. And we know that endomorphisms in A mod of A is a, there's some ups somewhere. Up? Okay. Okay, so when you look at this category A mod, you can also forget about, you can take the full subcategory generated by this one object. You get a category with this one object. That's a category with one object that recovers the algebra A. But this category A mod is somehow more natural than the subcategory with just one object. So we want to think of A mod as the category generated by the object A. Now, abstractly, if I just give you a category, if C is a category, how am I going to get an algebra attached to it? Suppose I pick an object M. So let's pick an object M in C, which is going to be an object that has some adjective in front of it. OK, it's called compact, but let's just not worry about that. We have an object C. So given an object C, we get a functor from C to vect, which is hom from M. And, but then you realize that the vector spaces you get at hom from M are not just naive vector spaces. They're modules over the endomorphisms of M. They have a natural structure of a, you can precompose with endomorphism of M. Maybe that gets them all. You can precompose with an endomorphism of M. So you get a natural functor from C to end of M. And if it's M is a generator if this map is an equivalence. So that's a notion of a generator. So that means that your category, so given a category and an object, you get an algebra. The object category is generated by this object if you have this equivalence. And this is pretty easy to verify. And so, so we can think of, well, the word generator says that it's an equivalence.
I think the question is whether C, you need C, for example, to have enough colimits.
Yeah. So the kind of differential graded categories, and well, with with all colimits.
So you already have things like direct sums.
That's right. That's right. That's right. OK. So that's the picture we're going to go between categories and algebras, and we can think of them as and in particular, this answer the questions. Yeah. This is a full subcategory of what? Of DG cat. Of this two category of DG categories, this is a full subcategory where I think to any DG algebra, I attach its category of modules. And then with appropriate adjectives put in front, the functors between those categories are exactly by modules. So I won't spell out the functors, but we can. This is what Morita theory. This is what Morita theory is about. That algebras, if you like, are just a specially kind class, nice class of categories. And so, OK. So, so for example, if I have a algebraic variety, if X is algebraic variety, you might look at some derived, some DG category, derived category of coherent sheaves on X. That could be my category. There's always a nice distinguished object here, which is the structure sheaf. And I can take hom from the structure sheaf, which is also the same as global sections, which is hom from the structure sheaf. And this goes to DG vect. And again, in fact, it'll go to O mod. Sorry, not O, what it's called. Global sections of O modules. And I'm going to, everything is always going to be a derived. So there's secretly going to be R's everywhere. So if you haven't heard me say derived, it's already been said once and for all. But this is not actually usually an equivalence. This thing is a generator if this is a generator if X is affine. So usually sheaves on a variety are not the same as modules over global functions. That's exactly the definition when I'm affine, but in general it's not. So that's going to be. So this is, if you'd like, well, OK, we'll return to that later. So OK, so that's an example of an object that's not a generator typically, but a relation between rings and sheaves. OK, so and again, all right. So then again, the rough idea. So again, we think of what we attach in our field theory to an n-2 manifold is going to be either the category of sheaves of some kind, and you can't ask which one because you didn't ask which kind of functionals I had before. So sheaves on some space of fields. And then again, the same picture is going to give me functors that if I give you fields on, I give you a Bordism between P1 and P2, I can write down an integral transform. Z of n is going to be P2 star of P1 star tensor some distinguished object, which is, we call it e to the is. And that's a map from Z of P1, from one DG vector space to Z of P2, which is an integral transform. If you like, you can think of this as being that there's some particular bimodule over functions on P1 and functions on P2, which are functions on the product, times e to the is. Okay. Functions on the product times this distinguished function. OK, so that's all right. So now we can. So now I wanted to state. Actually, what is my?
So the schedule has some flexibility in it, but of course your audience
Doesn't.
Needs some relief at some point. So I would recommend wrapping up soon, knowing that you have further lectures.
Yes. OK, let me just state the cobordism hypothesis in some rough form, and that's going to be our guide when we. So the cobordism hypothesis. Hypothesis is formulated by and Dolan and proved by Lurie, says roughly like this, says that a framed topological field theory, in other words, if I'm going to keep track of manifolds with framing, it's uniquely determined. It's uniquely determined by Z of a point. But really, maybe again, I'm going to think of this as being Z of Rn. In other words, i.e., so I'm going to introduce some very misleading notation. There exists some procedure, which I'll denote by m goes to Z of m, which is the integral over m of Z of Rn. Now, this notation has nothing more content than the cobordism hypothesis itself. The claim is the cobordism hypothesis gives you a procedure to start from Z of Rn. And uniquely, if you give you an n-dimensional field theory, it's uniquely determined by some procedure from Z of a point. I'll call that procedure integration. Now, moreover, given some object, given an object O in C and N category, symmetric monoidal n, given an object, I can ask, when does it work? And it says there exists an explicit, relatively explicit, increasing list of finiteness conditions. Conditions called dualizability, called K dualizability. T for K being, I guess, at least 1 and less than or equal to n. There exists a notion of dualizability such that that the integral over m, a K manifold of O, converges. So any manifold of dimension less than or equal to K. So there's a list of conditions that says that if I look at not and so I'm going to declare O to be Z of Rn. Given this object, I'm going to just declare Z of Rn to be the object O. And then I'm going to ask, can I integrate this on K manifolds for various Ks going all the way up to N? I'll say it's K dualizable if this procedure makes sense. And there's a list of conditions. And we know the answer is uniquely determined by that. OK. And so time for one more sentence? Yeah. OK. So just I want to explain one last thing about this chart. I'll say more about the non-framed version maybe next time. But the most important thing for us is going to be this procedure of compactification. Compactification that says that if I have M, a K manifold, and Z, an n-dimensional topological field theory, I can define an n minus k dimensional topological field theory. Let me call it Z sub m. where by just saying that Z sub m on any manifold is the original theory Z on m times n. So I'll define a new field theory, which is now only n minus k dimensional, by just declaring it this way. Now, by the cobordism hypothesis, this field theory is completely equivalent data to just giving Z of m. Because Z of m is what Z sub m attaches to flat space. So there's two equivalent points of view. You can either think we have a n minus k dimensional theory we got by just sticking in m everywhere, or we have a single object, what we attach to Rn minus k. So this is going to be the rule of the game here. When I write a manifold, we're going to decide whether we mean the field theory, which is compactifying on that manifold, or the object that you attach to that manifold, and we'll go back and forth. So that's why the numbering here might be opposite from what you think. If I plug in a 3 manifold, what I get left with is a 3-dimensional field theory. If I plug in a 4 manifold, I'm left with a 2-dimensional field theory, which I will think of as a category. So this row will be the row, very roughly, this row will be categories. Categories, this will be vector spaces. And this row, which I didn't leave myself any room for intentionally, is numbers. So that's it. Yes?
So just from the way you've written the Bordism hypothesis there with the value of Z on m is some integral over the points of m, the value of Z on a point.
Yeah.
That makes me think of Z evaluated on a point as being something like the impulse response of the linear system.
Sorry?
It makes me think of Z evaluated on a point as being like the impulse response of the linear system. And then I'm reconstructing what happens basically by integrating some general function times the impulse response or something like that. Do you think that's a proper analogy for?
That sounds great. I don't know what impulse response is, but it sounds. There's another word that physicists told me I should use there, and I. Okay, I'll remember. So yeah, there's something or other matrix. Okay. Yeah. Sorry. That. Yeah.
Framed just means this addition of the n minus k dimensional vector bundle, right?
Yeah, so framed means I'm always thinking of these manifolds as being n-dimensional manifolds, and I'm trivializing their tangent bundle. There's versions of this where I ask this field theory to only depend on orientation or only depend on spin, and that's going to be extra structures that I have to propose here. This is the basic thing, and now we can add the various structures if you want the field theory to only depend on the underlying, say, just unframed manifold. Yeah. But I mean, I might ask if the theory doesn't depend on just on having a bundle itself. I'm always going to think of these as manifolds with an n-dimensional bundle, but maybe I don't care about it being framed. I only care about it being oriented.
What's that structure group for theory X?
Well, I think we expect this to be, well, for the full superconformal field theory, I mean, in that setting, I'm assuming that I have a 2D conformal field theory valued in 4D topological field theories. I think these are going to be oriented. I expect these to be oriented topological field theories. So the field theories I'm going to be talking about, the 4-dimensional field theories, none of them will be framed. Yeah, I think that's. But there'll be subtleties. For example, you need this Friedwitten thing that it's really. You have this extra data on your manifold, which doesn't have the flavor of a framing. It has this flavor of this, this choice of Lagrangian. It's really a relative field theory. It has this kind of extra data, which you can think of in the same flavor as the manifolds do have some extra structure, but it's of a different nature. We're marking certain cycles. Yeah.
If I'm the type of person who simply doesn't know the meaning of pictures other than do my 2-gauge theory on 2 manifolds, what should I think of one of these type of gauge theories?
Well, think of gauge theory on 2 manifolds. Well, so next time we'll give the example. We'll start next time with over here, which is going to be a version of just 2D Yang-Mills theory. So it's going to be. So we'll explain next time usual 2D topological Yang-Mills, and that's going to and how that fits here. And over here we're going to have somewhere here we're going to have 2D the B model. So that's going to be the other example. Thanks.